Alright, today we're going to talk about acids and bases, and we're going to get into some of the definitions as well as do some math related to these concepts as well. Alright, first off with acids and bases, we need to think about a definition. And for definition, they're a group of chemicals that share certain characteristics, and we're going to actually have a couple of different definitions. They're common substances that you use every day. For example, soap, different kinds of juices, drain cleaners, different sodas, vinegar, and acids. All things that we see on a regular basis that have properties that allow them to fall into either the acid or the base categories. Now, for acidic properties, they will taste sour when you dissolve them in water. Obviously, we don't usually use taste to test chemicals in the lab, but substances that have that sour taste, many are corrosive and poisonous, hence the reason we're not going to taste them, and it will turn pH paper red. Okay, pH paper will be one of the ways that we will test these substances in the lab. And it also will react with metals to make hydrogen gas. Okay, so we've seen some of these substances take place, particularly in single replacement reactions, where metals above hydrogen in the activity series will go ahead and replace it. Okay, so for example, if you have barium, solid barium, you add sulfuric acid, what's going to happen is the barium is more active than the hydrogen, if you remember our activity series, so it will essentially kick out the hydrogen, hence the single replacement reaction. We get hydrogen gas and barium sulfate in solution. Now, continuing with acidic properties, they will react with bases to make salt and water. Remember, our definition of salt from a chemical perspective is really just an ionic compound. Okay, so you can have regular old sodium chloride table salt, but any ionic compound. And an acid is considered neutralized when it's added to equal number of moles of a base. Okay, and we'll see some of these in class as well. And it produces, like I said, an ionic compound, also called a salt, and water. For example, if you take hydrobromic acid, which is a strong acid, which should be a term we've heard of before, add it to potassium hydroxide, which is a strong base, which can also be a very dangerous chemical, you essentially get water, and potassium bromide, which are pretty neutral. They also will conduct electricity when they are in aqueous solutions, and that's because they have charged particles. Remember, an acid is something that usually has hydrogen ion, which we're going to come back to here in just a minute. Strong acids will conduct very well because they are strong electrolytes, which we should remember from when we covered solutions. Okay, they are strong electrolytes. Weak acids conduct a small amount because, if you remember, those were weak electrolytes. Okay, common acids. Sulfuric acid is used in car batteries. Nitric acid is used in explosives. You probably, hopefully, don't have too much of that, but we should know these common uses. Okay, this is something that we should be familiar with. Phosphoric acid, it's used as a flavoring in soft drinks. If you read some of your soda cans, you're going to see that it has phosphoric acid in there. Hydrochloric acid is the acid that's in your stomach. And acetic acid is otherwise known as vinegar. Okay, it's usually a 5 to 8% vinegar solution, with the rest being water. Okay, so things that we're really familiar with. Now, base properties, on the other hand, are going to be the opposite pairing here. Bases are going to taste bitter. Again, we're not going to taste chemicals in the lab. They're typically more caustic, so they can cause burns, so we usually don't taste to test these as well. They're going to turn pH paper blue, whereas acidic turned it red. They typically will feel slippery when dissolved in water, and you've all done this when you've washed your hands with soap. When the soap bar literally falls out of your hand, it just gets very slippery. Okay, so that's obviously not concentrated enough to cause a burn is soap, but that is a chemical as well. Similar that we saw with acids, they will react this time with acids to make salt and water. It's that whole idea of what's called a neutralization reaction. And we have the same concept of them conducting electricity, where your strong bases are going to be strong electrolytes and your weak bases are going to be weak electrolytes. So strong are better conductors, weaks are kind of in the middle. They'll conduct a little bit, but not super great. Okay, quick review here for naming of acids again. We've done this a lot, but for example, our binary acids are acids with only two different elements. It's usually hydrogen and another. It's typically a halogen. These are your hydros, and they end in ic. So you've got hydriotic, okay, We're just going to skip this one for right now because we're not going to really call that an acid. We've got hydriodic, we've got hydrobromic, you've got hydrochloric, and you've got hydrofluoric. Okay, now ternary acids or oxyacids, they contain 3 different elements, typically hydrogen, oxygen, and another. There are a few exceptions. No prefix, so no hydro here. The name of the polyatomic ion is what's going to drive the name of this acid, and this is where we go the whole ic for 8 and os for ite endings. Okay, for example, this is the perchlorate acid, so this would be perchloric acid. This is the so we go 8 to ic. This is phosphate, so this would be phosphoric acid. Okay, and here we have nitrite, which is at ITE, so this would be nitrous acid. Okay, again, review, but doesn't hurt to do it. Okay, we have some definitions here. Monoprotic acids are acids that only have one acidic proton. Now you'll hear us refer sometimes or a hydrogen ion. Okay, you'll hear us sometimes refer to a hydrogen ion as an acidic proton because if you think about hydrogen from a molecular level, hydrogen is number 1 on the periodic table. So that means it's going to have 1 proton floating around. It may have some neutrons, but in a neutral hydrogen atom, means you have 1 proton and then 1 electron floating around. Okay? Well, if the hydrogen gives away its electron, that's where the 1 plus charge from, so it's essentially a proton floating around in space, particularly if there's no neutrons there. So that's why we say acidic proton, which is the same as hydrogen ion. Okay, now polyproducts either have 1 or 2 protons or hydrogen ions, so it's going to contain more than 1 acidic proton or hydrogen ion. For example, you've got phosphoric, sulfuric, anything that's got that 2 out in front that can be split apart, you still would get 2 hydrogens from that compound as well. No, organic acids are something that contain what's called a carboxyl group. And we were learning about alkanes, the functional groups, but an organic acid is something that has a carboxyl group off of it. Those are typically very weak acids. Okay, now we got to talk about strong and weak acids. Now, strength of acids, first of all, does not indicate or influence danger. This is simply, or potential danger. This is just how strong they are. And what it depends on is the polarity and the strength of the bond holding the hydrogen to the rest of the molecule. Strong acids will ionize completely. They are strong electrolytes. And if they will ionize completely, these would have a weaker bond. Okay, a weaker bond which allows it to be separated. And would these have a polar or a non-polar bond? Typically they're going to have a polar bond because someone's going to steal the electron from the hydrogen, essentially. Okay, so you usually get a pretty weak polar bond where that electron can be sucked away. For example, if you have hydrochloric acid, okay, it's going to be polar. Here's the negative side. So if it splits off, you're going to get the chloride. It's going to steal the electron and be negatively charged, and hydrogen, and hydrochloric is one of your strong acids. Now, again, we've seen these in the last unit. In last unit, I didn't really make you memorize them. We got to memorize them here. There are 6 strong acids: hydrochloric, hydrobromic, hydriodic, perchloric, sulfuric, and nitric. And if they are not on that list, then they're weak acids that only ionize partially, meaning they do not split up as much. So for example, hydrochloric, every mole of hydrochloric you dump in is going to split up into hydrogen and chloride. Anything that's not on this list, okay, for example, hydrofluoric is not on that list. Well, if you dumped hydrofluoric into solution, let me get a bigger beaker here, some of it would split. But since it's a weak acid, a whole bunch of it would still stick together. And hydrofluoric is actually one of the most, it would still stick together, which makes it a weak acid and indicates the fact that it only ionizes partially. Hydrofluoric is actually an extremely dangerous compound, so that's kind of where I was talking about where strong and weak does not dictate danger, just depends on the chemical makeup. And we can, again, like I said, any acid not on the list above is going to be weak. Okay, now the strength of bases again will depend on dissociation and structure. Strong bases are strong electrolytes. They're group 1 and group 2 metal hydroxides. So you have any metal plus the hydroxide ion. So obviously any group 1, like potassium, would be potassium hydroxide. Any group 2, which has a 2 plus, you would need 2 hydroxides to balance that out. Okay, so barium hydroxide would look like that. There you go. Examples: potassium hydroxide, barium hydroxide. Weak bases are weak electrolytes. This ammonia, which is NH3. Okay, you got to just memorize this one. Ammonia is a weak base. It's the most common weak base that we're going to keep talking about in this unit. You can get some organic bases that are left over after something donates a hydrogen. We're not going to focus too much on this. Okay, now finally to our definitions of what acids and bases actually are. And there are two definitions we're going to have to be familiar with. Arrhenius is probably the most classic. It's also the most specific and the most exclusive definition. It was created by Svante Arrhenius. He was Swedish. He did a lot of studying with ions. His definition of an Arrhenius acid, all right, is a compound that creates hydrogen ion in an aqueous solution. So anything that generates hydrogen. Now, base for Arrhenius is a compound that creates or generates hydroxide in an aqueous solution. Okay? So here is just some looking. Now, Bronsted-Lowry is going to be a different definition. Bronsted-Lowry is a bit more general and a little bit more common. It's more inclusive here. Created by two scientists around the same time, hence they got both names. Now, an acid, the definition is pretty similar. A molecule or ion that's a hydrogen donor. Okay, so it's going to donate the hydrogen ion. A base is a molecule or an ion that is a hydrogen acceptor. Okay, so here's the difference right here is with the bases. Arrhenius said hydroxide. Bronsted-Lowry says hydrogen acceptor. For example, this you've got, if we look down here, hydrochloric plus water. This is the acid. Water is your base. That is going to act as. So same thing down here. Hydrochloric acid is what is donating the hydrogen ion to the nitrogen, or the ammonia rather. This is going to be our base. So the chemistry here is going to create the ammonium ion and the chloride ion. A little bit different than what we've seen. The limitation of Bronsted-Lowry is that it does not include strong bases because it does not have the hydroxide. Now we're going to look at some substances and determine if they are acidic or if they are basic. So what you need to do here is, I'm going to bring all these up and kind of talk through them. First off, on the very first one, you can go ahead and cross off the first one. There's a way to figure it out, but I'd rather focus on the ones that are more straightforward. So, all right, first off, the very first one, remember, we're trying to figure out what do we know about acids or bases. Acids, we're looking for hydrogen ion out front. Bases, we're looking for hydroxide at the end, or some of the weak bases that we just have to memorize. All right, so first off, we've got magnesium hydroxide. It's definitely going to be a base because you have the hydroxide, and it's going to be strong because it's a metal hydroxide. It's a group 2 hydroxide. Okay, this next one we have is hydrofluoric. I'm going to go ahead and do strong and weak as well just to give us some practice. It's definitely an acid because you have hydrofluoric because it's going to split into the hydrogen ion and the fluoride ion. And hydrofluoric is not on that list of strong acids, so it's going to be a weak acid. Okay, here we have ammonia. Ammonia was one of those weak bases that you just have to memorize. There's really only a couple of them that we have to memorize, and ammonia is one of them. All right, here we have carbonic acid, which would split up into 2 hydrogen ions plus the carbonate ion. So since we have that hydrogen out front, it's going to be acidic, and it is weak because it's not on the list. All right, sulfuric here, we also is sulfuric acid. So we have sulfate and hydrogen ion. So it is acidic and it is strong because it's on the list. Here we have another compound that ends in hydroxide. So it is also going to be a base and it's going to be strong because it's a group 1 hydroxide. Here it's potassium hydroxide. This is also one of those weak bases that I just asked you to memorize. What happens is it can accept another hydrogen right here, so it ends up as NH3 with a plus charge. Okay, or you can just memorize it, that H2 on the end can accept a hydrogen ion right there. This is acetic acid, so split into the hydrogen ion and then the acetate ion. It's an acid and it is weak. and this is hydriodic acid, which is also on our strong category. Okay, so there's our acids and bases, and I'm going to stop there, and in the next video we're going to talk about the pH scale.